That drink is really helping me. When I run out of my drink, then we're really screwed. then we'll have to like take a 20-minute break so I can go get a refill or something. Anyway. Yeah, so what do I want to do with this?
The x's are going to cancel out the minuses in the r exponent. Or
R minus 3 and 3, right, becomes x to the r. And this term also, x to the r. And this term, and this term. So you can just factor it out and get rid of it. Right? Just factor it out and get rid of it. So what you're left with then is just r minus 1, r minus 2, plus r times r minus 1, minus 2r, and then plus 2. What we have to look at here, this is going to be cubic. So we're going to have to hope this is one that we can find the roots of pretty easily. Right, because you have r times r times r. That's r cubed. And then minus 2r minus r, that's minus 3r. But there's another r here, so minus 3r squared. And then plus 2 times r. This is the part, guys, where you have to go slow and careful. Okay? It's worth it to get it right so that your life is easy rather than solving a problem I didn't mean for you to be dealing with. Here we have r squared minus r, minus 2r, and plus 2. Okay, so now, what can we do?
Combine the r squared.
Okay, combine the r squared. So I have r cubed. How many r squareds do I have? 2. Minus 2 of them, right? Minus 3r squared plus r squared, that's minus 2r squared. Okay, what else?
Minus 1r.
Minus 1 factor of r, and plus 2. Okay, and I'm kind of being bad here. This is supposed to be an equation, so they should all be 0. Okay. So, this is what you end up with. So I gave you my little tip earlier. The roots, if they're going to be rational, have to be divisors of this number. So the only possible roots are 1 and 2 and negative 1 and negative 2. Right. So you could just go through and check all 4, see which ones work. There's got to be a total of 3 roots, by the way, including possible repeats. Remember, some of these roots could come up more than once. There's nothing that says you're going to have all of those roots. The candidates for the roots are those 4 that we just listed. But they may not all be there. So you could just test them. Like you could plug in 1. 1 minus 2 minus 1 plus 2. It seems to work. So 1 is a root. But there's actually another way to actually, before I just start writing down the roots, does anybody see another way that you can actually factor this?
By grouping?
By grouping. And I guess that's what they call it in the high schools.
That's how I learned it.
That's how you learn it. So by grouping, so can you tell me what you mean?
So you could take, so the first 2, you take like each part independently. So the first 2 you can take out x squared.
Or r squared, yeah.
R squared, sorry, yeah, r squared. Which gives you r minus 2.
Okay.
And then the second part, including the negative, you can take out just negative 1. And, yeah, there you go.
Like that, right? Mm-hmm. And then the factored piece that came out of the grouping is common, both here and here. So now you can pull that out. R minus 2 times r squared minus 1. And so now you've got everything down to just quadratic, or easier. So what are your roots?
2 negative 1 plus minus 1.
Mm-hmm. So 3 different roots. If this had been a constant coefficient differential equation, our solutions right now would be e to the 2x, e to the x, and e to the negative x. But remember, we're not solving a problem that we are familiar with. We're solving this one here, where our solutions have this form. So don't forget to go back to here. Okay? So we get 3 solutions. We get y1 of x, which is x squared. We get y2 of x, which is x. And we get y3 of x, which is x to the minus 1, which I'm going to write as 1 over x. Okay? Yeah, so
On the sample test, you just said find the real roots. So we didn't have to do that on that one?
find the real roots.
Yeah.
That's what we just did.
So that would be just the answer for that one?
Oh, yeah, I guess so.
Okay.
That's right. On the sample test, I just wanted the values of R, and then you could just stop.
But you also find the values of T and then.
Later on, yeah, there's like multiple parts there. Yeah, that's a really good
Yeah,
question,
yeah,
by the
right.
way.
What happens if we find repeats?
Then it's not going to work in this context. Because we know what to do with repeats in the problems that we looked at. But this is, again, a theory we've never looked at before. So, you know, when you have repeated roots in our context, you start stacking those powers of x in front of the exponential terms. Well, we don't have that here. So I couldn't have asked you that. I actually think on that sample problem, that does happen.
There was a bunch of twos and we just didn't do anything.
So if you haven't done the sample test yet, you're going to see this come up. And, you know, where there is, basically if there's a repeated root, I'm going to have to explain to you how to deal with it. It's not going to be something that you would have already known how to do. Yeah, we go.
So, what exactly, what chapter is this from?
This is still from chapter 6. We're still talking about, it's really, okay, here's the thing, guys. Here's chapter 6. And here's my point. Everybody gets too wrapped up in these two sections. Everybody gets too wrapped up in annihilators and variation of parameters and the procedures of solving those problems. But I want people to also understand the underpinnings of what you're doing there. So sections 6.1 and 6.2 address things like linearly independent solutions, how you derive those basic solutions, and how you write down the general solution. So specifically, Miguel, this is coming from section 6.1 and 6.2. Okay. So we have 3 solutions here. So then our final answer for the general solution, let me write that down. The general solution would be C1 x squared plus C2 x plus C3 times 1 over x. Okay.
Oh, so then going back to his question about the repeated roots, if we do got repeated roots, you're going to tell us how to put it into the...
I'd have to tell you, yeah, because it wouldn't have been anything we ever covered.
Okay.
So, and that's what you'll see on that sample test.
Yeah, the sample test just asks for a real number such that like T.
Yeah.
I basically already gave you the form of the solution that you were supposed to have.
Yeah.
And so all you had to do was come up with the scalars.
Okay.
Yeah. Is this all we need to do here?
Yeah, you have to check for linear intervention.
Right. Make sure you read these questions carefully. Question says check for linear independence. So how do we do that? Right, exactly. So, and of course we have 2 different Wronskians that we've learned about now. One for vector functions in chapter 7, and one for scalar functions, which is what we're doing right now in chapter 6. So these are scalar functions. So you have to remember how to do that Wronskian. The Wronskian, pardon?
The derivative one?
Yeah, it's the one where we take derivatives. So we're going to take our 3 functions, which we've already written down, and we're going to take the determinant of... Okay, just to remind you again, the way we do this, we put our functions on the top row, and we start taking derivatives straight down. Oh, by the way, now you kind of know why it said x greater than 0, because you're getting x's on the bottom here. Okay, so the derivative of that is going to be negative 1 over x squared, and the derivative of that is going to be 2 over x cubed. Okay? Just using my power rule. Make sure you differentiate, don't integrate. Okay?
Isn't the derivative for that one 2?
Yeah. Oh, 2. Yeah. Blame it on my throat. There we go. Okay. Right. How are you going to do that determinant? Go back to expand the last row. That's fine. I probably would use the arrow method. The other thing you can do, if you want to feel lucky, is you can just choose a value of x right now, put it into all 9 entries, and see if it gives you a non-zero determinant. So let me just remind you, the Wronskian test says, especially when they're telling you, there's no question what the right answer is. You know these are going to be Li, so there must be some value of x that would work here. But you have to be careful. You have to choose a positive x. Or you can do cofactor expansion. Maybe we should do cofactor expansion. We're still having a lot of people really struggling with cofactor expansion. Guys, be looking out when you're doing cofactor expansion. You don't have to use the first row or column. You can use any row or column, but make sure that when you choose a row or a column that you go all the way across that row or column. Don't just take don't take just one entry. I'm thinking especially for the eigenvalues, right? You sometimes have multiple terms and you can't avoid it. Okay, this is an example of that. No matter which row or column you pick, you will have at least 2 terms that you have to write down. So I think I heard people say the bottom row.
I think the middle column would be easier though.
Middle column,
X1
okay.
and 0.
Let's try the middle column. I'm fine with that. So the middle column, remember what you do. You take the entries from that column times the cofactors from that column. So the entry here is an x. To get the cofactor, I cross off the middle row the middle column and the top row, and I've got these 4 numbers here, right? And I just do my little 2 by 2 submatrix. This times this minus this times this. So this is going to be 4 over x squared, and then plus 2 over x squared. Now what I need is somebody to tell me what I did wrong.
Minus sign.
Your x is negative, yeah.
There.
The
4 over
Oh,
x
is that-
squared is 4 over x cubed.
4 over, but it's x over
Yeah,
x
that's
cubed.
right. That's right.
It's x
Oh,
over
okay,
x
okay,
cubed,
okay.
so it's over x squared, right? But I did do something wrong on purpose, which is,
X is negative.
right, that's a negative position. Remember, okay, camera people aren't going to get this one.
So sad.
Yeah. Don't forget, you got to keep track of where are you in the matrix.
Do you want me to just point it real fast?
Sure, go ahead. You have excellent camera crews here showing the positive and negative cofactor thing that you have to remember which terms to change signs for. Thank you. Okay, so we have that. Then the next entry, which is a positive 1, gets multiplied by, I guess it's the determinant of the 4 outside corners, right? So x squared times 2 over x cubed, which would be 2 over x, and then minus, 2 over x, okay? Actually, that term is going to go away. And this is actually just 6 over x squared, so negative x times 6 over x squared, which is just negative 6 over x. As long as that is not always 0, then the Wronskian is not 0 and the functions are Li. So the point is this is not 0 for any positive x.
So if we were to plug in just the number for x in the beginning without doing the cofactor, and let's say I chose x to be 1 because it has to be greater than 0,
You get negative 6.
and I get negative 6, and then
If you chose x to be 2, you would have gotten negative 3.
and I'd just be done after 1?
Yeah.
Okay.
The advantage of, okay, time for a little pros and cons thing. The advantages of plugging a number in for x at the beginning are then your matrix is just all numbers.
Yeah.
The disadvantage is you could get unlucky and you happen to pick an x. I did this on the quiz on purpose. I made 0
Yeah.
not work out so well. You could get unlucky and pick a number that gives you a Wronskian of 0. And that means then you've got to go back to the drawing board and try a different x. So if you're able to handle the general expression, then you'll know what this comes out to, and you don't have to sweat it.
Like you mentioned the quiz, if you do get a Wronskian that equals 0, you know that that's wrong because there's supposed to be a line.
Well, on this problem they are, yeah. I don't remember what the quiz was, whether they were,
I don't know.
if they were not necessarily known to be LI, then,
Then you're just.
yeah, I think on the quiz I said, are they LI or LD? And you had to circle the answer,
Yeah.
right? So you actually, it could have gone either way on that one. So, but remember, if you plug in a value of t or x or whatever, and you get 0 for the Wronskian, you're not done, right? Because unless you know that for every value of t or x or whatever, that you're going to always get 0, then it's possible that you just picked a bad choice of x or t, and if you try another one, maybe it will work, right?
Now, how do you know when you should try another one?
If you get 0 for the Wronskian. Okay, let me be a little clear about that.
I have one more.
If, just a second, I want to try, I think I know what you're getting at. If you plugged in, if you did what Sarah J wanted to do, and you plugged in a number here originally, and then you got 0 for the Wronskian, then you need to go back and try another number. But if you leave it in terms of x's, and let's say that you don't plug in a number for x, you just leave it in terms of x, and let's just say that the Wronskian comes out to that, right? Now you're looking at that and you're saying, wait a minute, doesn't matter what x is, because I left it very general. If that's my formula for my Wronskian, I already know I have a trig identity, sine squared plus cosine squared is always 1, so this will always be 0. Then you don't need to plug in different values of x, because you just did it for a general case. See what I mean?
Yeah.
It's when you plug a specific number in and then get 0 that you have to stop and say, oh, I might have gotten lucky or unlucky, I need to try another number. Now, if you plug in a specific number and don't get 0, then you're done. It's linearly independent, right?
If you plug in a number, you get 0, and then you go back to it and plug in another number, you get 0 again, LD automatically? Or you just, okay.
You gotta keep doing it until you start to realize that I'm getting 0 every single time. Maybe I should leave it general
And then,
and work it out and see that it's always giving me 0.
okay.
Guys, if anybody does this on the test, I'm going to freak out. If they try 10 different values of x and they get 0 each time and then they tell me that it's LD, A, you wasted a whole lot of time, and B, you haven't convinced me yet. So you're better off, in that case, after 1 or 2 tries, you're better off just doing it for general x. Don't keep plugging in numbers for x. Your whole test period will go by, and you'll still be doing it. Right? Because there's a heck of a lot of numbers out there that you could plug in.
So the max you would try is just 2.
Probably.
Go back.
That's, yeah, I mean, there's no hard and fast rule about that, but yeah, if you've tried 2 different values, chances are, if you're getting 0 twice, it's probably always 0.
Okay.
I'm not saying there couldn't be an exception to that, but that's a pretty good rule of thumb.
Okay.
Okay. Okay, let's move on. Everybody doing okay so far? Okay. Okay, let's do number 7, the one right before that on the sheet. So, show that x e to the x is an element of the kernel of L, where L is negative d squared plus 2d minus 1. Does anybody know which chapter this is from? Test only covers 5, 6, and 7. 6. It's chapter 6. Kernel of L. L is a, see the d's, those are derivatives. So this is a higher order, because it's d squared, so it's second order differential equation, right? In fact, if you write down what L of y is just negative y double prime plus 2y prime minus y. Oh, you know, that's really important. A lot of people make a little mistake here on this. This minus 1. Down here, when you plug y into it, it's not minus 1 anymore. A lot of people like to write that down. But that's not right because it's 1 time. See, you're actually applying this thing to y. So it's negative 2 derivatives of y plus 2 times 1 derivative of y minus 1 times y. If you write that out like that, you won't make a mistake on it. Okay? All we're doing right here, and it wasn't really what we were asked to do, but we just took the operator L and we rewrote in sort of more of a concrete form what is the dE that we're talking about. And this is it right here. Now if I'm in the kernel of L, so y is in the kernel of L, what does that mean?
L y equals 0.
Good, L of y equals 0. So if I plug in the y into the L operator, I'm supposed to get 0. So all they're really asking you to do here is check L of x e to the x. And we've already got the formula right here. So it's negative 2 derivatives of it plus 2 times 1 derivative of it minus x e to the x. And the question is, show that it is in the kernel. So this should be 0. You just have to show that it is. Okay. So you might want to go over on some scratch work to write down the derivatives. You're going to have to use the product rule, right? This is actually not a very hard problem. It's just a matter of working that calculation out. It's not too much theory here. Okay. So x e to the x prime, excuse me, first term times the derivative of the second, plus the second term times the derivative of the first, and then x e to the x double prime would just be the derivative of that, which is just x e to the x plus 2 e to the x. But you guys make sure that's right. Once you got that, it's just a matter of plugging everything in here. Oops, I made a mistake, didn't I? This should be plus 2 times the derivative of that term. Okay, so here we have minus x e to the x plus 2 e to the x, and then plus 2 times x e to the x plus e to the x, and then minus x e to the x. And you just have to make sure that everything cancels out. Which it does. Make sense? Yeah, Curtis.
Is there an alternate way to solve it where you solve for d? Like
D is not something that you can solve for. D is an operator.
Okay.
D is not a number. It's not a matrix. It's
I think I kind of misspoke. I mean, like how we've been converting the d to like r. So like for example, you would get, if you factor the negative, you get r squared minus 2r plus 1, which is r minus 1 squared. And then you know that you get 1 twice. So you would get c1 e to the x and c2 x e to the x.
good point. So this particular differential equation is familiar enough that you already know what the terms in the complementary solution will look like, and you know that this is one of them. So you could just state that, which would be great, but you should be able to do this, because if I give you a differential equation that isn't familiar, then this is the process that you would use to solve it.
Okay.
Another thing I could ask you for right here would be, I could ask you to give me a second solution. This would be a good follow-up, actually. All right, so we found one solution that was in the kernel of L. I could ask you to give me a second linearly independent function that's also in the kernel of L. And that's where we would notice what Curtis said, that the auxiliary equation has the roots 1 and 1. So there should have been, so if I think if this is like y2, then e to the x should also be in the kernel. Right?
When you distribute those out, wouldn't you be left with a 2x in the x?
It all cancels. The algebra all cancels out. Minus 1 here. These two are both subtracted, and here's positive 2. And this negative 1 cancels this positive 1. I'm gonna let you work on that because I want to get back to my point. So if I actually asked you for a basis for the kernel of L, you need to remember that the kernel does form a vector space and that its dimension is equal to the order of the differential equation. So this is second order, right? So you need two linearly independent solutions in order to have a basis. This is sort of tying back into the vector space stuff from earlier. It's never too early to kind of remember how that works. So I have a two-dimensional vector space here. The kernel of L is a vector space. Its dimension is just the highest power of D, which is 2. So if I can come up with two linearly independent vectors, then they also span the space, so therefore they are a basis. And so here's one that was given to you in the question, and then Curtis realized that we could have written down another one because this is a familiar differential equation. And this one and this one are clearly Li. Or if it's not clear, we can use the Wronskian to confirm it, right? So we'll get, but it is clear because there's only two of them, and with two functions, if they are not scalar multiples of each other, then they must be Li. So you've got a basis, therefore. Basis for the kernel of L. This was not asked for in the question, but it's just adding a little bit. The basis for the kernel of L would be that set right there. Those two scalar functions. Okay? Make sense? Okay. Can I erase over here? Nice thing about having it on video is if I erase something, go back through on the slide the time back, and it'll reappear. Okay, I've got a couple more things I definitely want to go over, and then I may not go through this whole sheet today just for the sake of my own voice, but I think we're getting a lot of things done. I want to do number 6, 6C, I believe, on the review sheet. It says solve y double prime minus 8y prime plus 17y equals e to the 4x times the cosecant of x. Okay? This is something we haven't reviewed yet today. So, is it a system of differential equations or is it one differential equation? It's just one. So we're not talking about chapter 7. Is it first order or is it higher order? Higher order, so we're not talking about chapter 1. It's second order, so it's actually from chapter 6, where we talked about higher order differential equations. So we want to solve it. And it's constant coefficient, standard looking equation. So we've learned two ways to approach those. What are the two methods?